Thank you very much, Wojtek, for inviting me. Thank you all for coming. I want to tell you a little bit about a problem that I've been thinking about lately. Let me start with the problem, tell you why, and eventually I hope we are able to see these purple colored things. I realize the color choice is not so good. Hopefully I won't be using too much of it through the talk, but I'll try to read those out to you when I go on. This is joint work with a graduate student, Brendan Juba, who's at MIT. And the theme is to talk about this fantastic setting. So Bob's sitting at his computer and he suddenly gets a beamed some sequence of bits from a alien. We'll call her Alice for today. And now he's wondering, it's a sequence of bits. He doesn't know what it means. He's trying to figure out what should his response be. And if there are further messages, so he sends some response maybe, and she reacts in turn. How does he know? Is she really reacting, or is it just continuing with the existing sequence of transmissions that she was making anyway? How does he detect these things? And is there really an intelligent person out there, or are you just talking to some sunspots? And the thing that makes it all very interesting and non-trivial is that there is absolutely no common language between, there is no common background between Bob and Alice. If they want to make some assumptions, we have to state them very precisely and figure out what is the common assumptions, but really have to go very little to go by on. And so is meaningful communication possible in this setting? I'll try to come up with some answers to this thing. Just to sort of stress that this is not completely a problem of my own concoction, when apparently I think it was a Pioneer that was sent out to, it was an unmanned spacecraft sent to Mars to explore it. They're sending this huge satellite, but in addition they wanted to send a message which somehow conveyed something interesting to the Martians, and they put that as the faceplate on the satellite. So picture of a man, a woman, some planetary configurations telling them that we are here, etc. But really, does this convey information the way they expected it to? What assumptions are they making about the Martians in order to suggest that this is really us, and that's a friendly sign as opposed to we'll shoot you or kill you? And so what are the assumptions, what are the implications, what commonality are we assuming? And these are really fundamental questions, and I want to get to these today. But my goal is not to put something on the faceplate of another satellite. It's something different. I think that this is a question that comes up as a central one in modern computational infrastructures. Today we no longer think of the computer as a standalone object trying to compute a given function on a given input. Its role seems to be more or less to act as a enhanced cell phone. It's a communicating device. Its entire role and purpose is out there to be able to talk to all the other computers out there. But interactions between these computers are getting increasingly complex. And just to sort of, how many times my machine goes out per week to update some software or some such thing. Why? Because something has changed in the universe that it's interacting with, and it needs to know about it. And you're going to be perpetually facing this problem, because there are, if there are n computers out there and a new one coming every day, each pair you have to sit together and figure out how they're going to talk to each other, and somebody has to tell both the parties this is the language in which the two of you should communicate with each other. This is today I think we have a feasible solution for it in the sense we are able to do it, but I don't think that this is a great model for the future. In the future, we cannot afford to keep uploading new software every time something changes in the universe. Rather, we should be trying to understand how to achieve this interaction. Maybe it's even okay to upload software, but we should really be very firm and clear about what are our goals and how are we going to do this. And that's the issue that I want to talk about. There's some precise reasons listed over here. Basically, I want to suggest that the way computers talk are very different from the way humans are talking. Humans don't assume a total perfectly matched common interface. We assume some commonality and then build upon it. And the question is, can we do this? Can computers interact the way humans do? And this roughly takes us to this extremal setting, but let me sort of stress this point again. This is the reason computers and their interfaces are built the way they are right now is not because we are making compromises or we have perfect solutions and we just don't want to spend the time and energy that it takes to implement the perfect solution. I claim that this is a really inherent problem. There is an inversion of quantifiers. When the way we build interfaces is you're given two objects, computer 1, printer 2, and they want to talk to each other. And so we design a common language and say, well, look, this is the interface by which they should be communicating, this is the language, this is how you tell that this is a file to be printed, etc. And the person designing this knows what is the object that wants to talk, and knows the object that is being talked to, and understands this setup completely and then designs it. But really we want to flip quantifiers. I mean, when I buy a computer, I don't assume it knows about all the printers that are going to be manufactured in the next 2 years, assuming my computer is going to last another 2 years. So what do I expect? But I expect, look, it doesn't know, but it should be able to talk to them no matter what comes. So really our model that we are hoping for today is that when I buy the computer, it knows its interface, it knows how it's going to talk to the others, and then some object will come and then it will go off, another one comes, still is able to use the same interface, talk to it, and you keep doing this and it works. So we want really a single interface which will work for all these second class of objects, and this should be built when the object 1 was constructed. Okay, that's roughly how we are hoping things will work, and the question is, can we make this happen? So can such an interface exist? What should it, how should you go around building it, and what's the common assumptions we need to make? When we started this examination, we were really thinking, so let's try to see how many common bits of information do Alice and Bob need to share in order for this kind of an interaction to happen. After a while we realized that you can't really measure this. There is a 0 or a 1 phenomenon. Either they understand each other perfectly and we are going to build on it, or you have to assume or allow for the possibility of complete lack of understanding. So we tried to see what could we do in the other case, where we have complete no prior background, and see if we could do anything there. So this is going to be a theoretical problem from this point on. We're just going to be musing about it, but still I want to be able to talk about this. The motivations do exist, but till we find the perfect solutions, we're not going to solve the motivating problems. So don't expect a solution to the printer problem, but at least let's see what kind of questions we should be asking in this setting. So the goal of this talk is to mostly give you some definitions saying what is successful communication, okay? And the goal should be I want the goal to be laid out so precisely that I can prove a theorem saying if Alice and Bob are intelligent and cooperative, it's certainly possible that Alice doesn't want to talk, and then to be able to insist that I have to be able to communicate with her is impossible. Similarly, it's also, if they're not smart enough to be able to communicate, maybe it's not possible. It's a rock sitting there, can't already start talking to Mars right now. So they have to be intelligent, they have to be cooperative, but then communication should be feasible. So this is the theorem I am going to prove, but of course it's again just saying that there are more terms that need to be defined. What is intelligence, what is cooperation? And we'll define it in our context so as to make sense. And that will be enough for us to be able to prove this theorem, and in the process of proving things we'll be seeking what are interesting things that can happen, what are phenomena, what are protocols, how do you affect communication. And so this is something that I'll actually skip the method for proving or verifying intelligence. I'll be very happy to talk to some of the people offline about it, but we have some ideas on those as well, roughly because we have to start encountering this question, what is intelligence and what do you expect? So let me start with the first attempt at a definition, and the point of this slide is twofold. Firstly, I want to explain the difference between a sequence of bits and its meaning. Okay? What I can transmit to you, what I can receive from you are sequences of bits. I can never ever tell you what it means. If I try to tell you what it means, it will be another sequence of bits. Okay, so anything that I can communicate in this universe is just bits. What is there in my head is meaning. So how can these two differ? What's an example? Let me take the simplest example of a situation where bits carry meaning, and for this I'll use the Turing's model of the universal computer. So A sequence of bits is not just data, it could also be a program, and that program is its meaning. So thereby I am sort of associated with every sequence of bits a meaning. This sequence of bits is telling me to do something, carry on a sequence of computational actions. So in order to associate this meaning with this sequence of bits, I have to have a programming language in mind, a universal computer. So I have one. I am Bob. I have an association which says this sequence of bits is this sequence of actions. Okay, so I hope this makes sense. Alice has a similar language. She associates to a sequence of bits some meaning. That meaning is again saying this sequence of bits is telling me to do some things. But we have two different programming languages. We have no idea what the other person's language is, and that's what we are trying to learn roughly. So this is how we differ, and maybe we'd like to learn each other's language. Maybe that is a goal of communication. I would say that this is a little too naive. It's a first attempt. It is not going to work. But let me tell you the good news already. There is something good, which is that actually language learning is actually only a finite task. In order to tell you what Alice's language is or what Bob's language is, all I have to do is give you a compiler which will translate her sentences into your sentences. Okay? And that a compiler is a finite length string. If I tell you that along with the associated implications that this means something, then you are able to convert every sentence. So even though in her language she has infinitely many different programs she can write, there is one finite program, the compiler, which suffices. So it's only a finite sequence of bits. Why don't we just go ahead and enumerate all the possible bits? At least that would give us a weak, if not weak solution. The bad news over here is that there is no third party over here to give us the finite string. So Alice is on Mars, we are sitting here, nobody knows the two languages together to say how to translate one to the other. We don't have this person available, and that's the key issue. There is no one to translate from one language to the other. And I can try enumerating, say maybe she's working with C, maybe she's working with Fortran, maybe she's working with Pascal. I don't know what languages exist. I can try all the languages, but I have no idea if I'm guessing right or wrong. If I could at least, given a candidate hypothesis, say here is how I can prove this is right or wrong, that would be great. So turns out that this definition is fraught with a problem, which is that there are just indistinguishable possibilities, and I will never be able to distinguish them. And if I wanted to prove an impossibility result, I could take this result and be happy. But that's not our goal. Presumably we think there's something more. We do talk to each other. Children grow up. You could say they actually have a hardwired notion of language built into them. It's completely conceivable that that's not it. They just have good computing power, and eventually they learn human languages because they're interacting. So merely by the process of interaction, maybe you can acquire language. So there is some way of enumerating possibilities, figuring out right from wrong, and we have to understand what is that, not come up with this thing saying we can't tell the difference. That's not what's going on. So I claim that the indistinguishability of right from wrong is because we haven't even specified a goal for what communication is. So if you ever say that our goal is to communicate and that's it's never going to work. And instead you ought to have a goal when you try to communicate. I'm trying to achieve something by talking to others. My goal in communicating is not just a mere futile exercise in trying to understand something internal to your state of mind, which is infeasible in any case. Instead, my goal is to achieve something concrete and tangible and measurable in my sense, and if I start putting that in front of my objectives, then I should start being able to understand how to achieve these goals. So, but what are these goals? And it came as a surprise that nobody, at least in the technical literature, I'm sure there were philosophers and linguists who had been looking at this question before, and some of the people in the cognitive sciences, but in the setting of in the technical world, in the computer science literature, we and the communication literature, we did not see an articulation of this question. Why are we building these computers that communicate? What are they hoping to achieve by this thing? Okay. And once you ask this question, so the moral of this slide is just to say that communication is never an end in itself. It's always a vehicle to do something else, and we have to focus on that something else, figure out how to do it, and then whether you achieve understanding or not may become irrelevant. If you can still achieve the goal, why do you care? And it may actually give you understanding when you sort of try not to attack the question head on, but rather tangentially. So that's the way we are going to plan to do it. So I'll try to explain to you what are computational goals. I'll try to do it by an example. Okay. One example which I'll work with for a while, it will be an example from based on computational complexity. Before you dismiss it as saying, well, but that's not really realistic, bear with me, do pay attention, and at the end I'll try to explain why this is actually a little bit more broader than the way we are posing the question. But I want to understand this was really a serious issue. After we started looking at this question, I said, why am I interested in communicating? Okay. As there are clearly some instances I'd like to be able to effect some actions. I forgot to return the book to the library. I call up my assistant and say, look, there's a book in the library in my office, can you please return it to the library, it's due today. So this is what is an example of what I call remote control. So I'm using my communication to effect an action in some remote location, and certainly explains a large body of communication that we do, but that's not it. There's also intellectual communication. I'm sitting here, I'm giving a talk, you're listening to me. What are your goals? What do you expect to get out of this talk? What are my goals? Why am I giving this talk? And it's clearly not remote control. I'm not asking you to pick up your coffee cups and drink now and so on. So really, there's something else that goes on. What do humans expect to gain by communicating with each other? What do intelligent people expect to gain by communicating with each other? And I'd like to suggest that maybe it's a way of making progress intellectually. You tell me, give me some bits of information which I can use to solve some problems that I haven't been able to solve earlier. So a mathematician, a number theorist and a cryptographer get together, they talk to each other, they somehow suddenly find a new solution to a problem that neither one could have solved. So there's some intellectual development that's going on, and that's the kind of thing that I want to focus on in the computational goal. Here my goal is, as Bob, I'm sitting here, I'm trying to solve some hard problem. And Alice is out there, she's really, really infinitely powerful, and she's willing to help me. And I'd like to use her help and solve this problem. So what kind of problems? So I'm going to cast it in the language of computational complexity. There's a hard computational problem that we want to solve. So for example, Alice Bob might be wanting to run, get a good antivirus program. So he'd like to find out which programs in his computer are viruses and which ones are not, seeks advice, goes to Microsoft and say, give me some wisdom. And you could say, well, how feasible is this to solve the problem? Can you just go ask Microsoft, or can you go ask some other random smart person, and trust their advice? How vulnerable do you become? How good is this as a moral, as a motive? Should you go ahead with the advice given by these antivirus programs? So similarly, you can try to tell if something is a spam email or not. You can ask for advice on what's the next move to play in chess. You're just playing Kasparov and you have this remote, this cell phone sitting in your pocket, and you're asking other people, give me the next move, what should I do against this guy? Or you're just trying to solve some hard number theoretic problem, have a number A, I want to find its factors, so I ask the question, does it have a factor between x and y? So these are problems that I might want to solve, and Alice is out there willing to solve any of these problems. Problem is, she has no idea what I'm asking. Okay? I have to find her help, and I have to somehow figure out how to solve this problem. So can Alice help him? And just a quick sort of a primer on computational complexity. It's not particularly crucial what these are, but I hope people are familiar with P, the class of polynomial times solvable problems. This is what we think Bob can solve on his own. If he's going to get Alice's help to solve problems in P, he might as well forget it. He could just solve things on his own, and if that's all that he can do, then it's not worth it. If he can solve problems which are harder, like for example, if he wants to figure out whether something is a virus or something is a spam filter, these are uncomputable problems. He could not solve them in any finite amount of time on his own, but maybe with Alice's help this could work out. On the other hand, maybe he wants to solve chess, which would be a problem in P space over there, which is problems that can be solved in polynomial amount of space. We don't have that much time to solve every problem in this class, but it's certainly something useful, and NP is something that sits in between. So this is sort of as I go down this list, the problems are getting increasingly complex. The first line is what Bob could do on his own, and if Bob can solve any of the problems lower down with Alice's help, then communication is helping him. Question is, can you actually move down? Can you solve the virus detection problem with Alice's help? Wouldn't that be great? Can you solve P-space problems? That would be very nice too. Can we solve NP problems? So how much more can he expand his power? By interacting with Alice. And if you can solve some harder problems by interacting with her, you have gained something. Okay? Of course, now she's doing all the work. She's the one putting in all the effort to solve all the hard problems, and you might say, well, is that realistic? But we'll postpone that question for now. We just focus on this. So which problems can you solve with communication? Whoops. I have okay, so let's see if I can try something here. Sorry. Sorry guys, I'll just try this one time. I agree, of course. Okay, it's better. So sorry about that. There was some stuff that we had worked on, installed, and then it went back to its old state. So Bob's trying to figure out, so he has this problem defined by a set of instances that he wants to recognize. He has an instance of the problem, X. He wants to know, is X a good instance or not? So X is the program, is it a virus or not? Or X is a configuration on chess, and he wants to know whether it will allow him to win at the end or not, etc. And the way he could work is, Bob lives in the current universe, so he can do feasible computation. He can also toss a few random numbers. He tosses a few random coins and then starts interacting with Alice. He asks her a question, gets back an answer, and keeps going on, asks her questions, gets back answers, and at the end he has to decide. So based on this interaction, is X in the set or not? Okay. So he wants to solve the problem at this stage, and the claim is that at this stage he shouldn't just take the first bit of answer that she gives, but rather try to come up with a fixed function saying, I'll apply this function, and this function is something that I can compute efficiently. It should be a function of his inputs X and R, the answers that he got back from Alice. If its function says yes, that means X is in the set. If it says no, then at the very least he should not come up with the conclusion that X is in the set when it's not. Okay. So if you are thinking of the class of safe programs to run, you come up with a thing, you run this program for this interaction. At the end of the interaction, you should be convinced that this is a safe program, if it is. On the other hand, if it is not safe, then at least you should not come up with the feeling that it is safe. You should just come up with a question mark saying, I don't know. So the only time that this function comes off with a 1 is when the program is safe. That's what we would like to happen. But recall that all of this is happening with an Alice who has no clue what's going on in Bob's universe, doesn't know what the set S is, doesn't know what's going on, but she's willing to help. Any question Bob asks, she'll answer, but we cannot put any semantic association saying this is what she's saying. That's up to us to figure out. So this is the problem that we want to solve, and again, the question, which class of problems can you solve? What's the class of sets that you can recognize this way? And now this comes back to these questions. So what is successful communication, what is intelligence, what is cooperation, and let me try to define those things for you. Intelligence and cooperation is sort of, it turns out to be all straightforward once we are, look at it carefully. It's clearly impossible to solve this problem if Alice cannot decide membership in the set S. Bob cannot decide membership, Alice cannot decide, who's going to be deciding it? Somebody has to be able to do it. So intelligence, we have a clear criteria. She should be able to solve this problem that we are not able to. So it requires a little bit of a superior intelligence out there in order to be able to communicate, though this is something that we can get around. Then it's no good if Alice can solve all problems but always answers in monosyllables and always says yes to every question. Okay. So if the question answer response is not telling you, convincing you that she is intelligent, then there is no point in her being intelligent. It's not an internal state of mind, of Alice's mind, that we are interested in, it is what she can say. So she should be able to communicate this to you. And how do you articulate all this? How do you capture all of this? Here is a formal definition. So we say that Alice is helpful for solving the problem S if there is some person who can talk to her, not necessarily me, Bob, who's trying to talk to her, but someone else on her own planet, but they should be able to talk to her, pump in a sequence of bits, get out a sequence of bits, and at the end solve the problem. Okay? So Bob can talk to her, Bob B prime can talk to her, and that Bob B prime is no more powerful than us. He's also probabilistic, polynomial, time bounded, and the interaction between Alice and Bob is satisfactory to Bob B prime if and only if X is an S. So somebody speaks her language and is able to talk to her. Okay? So now there's only one. So this is a minimal restriction for us to be able to use Alice to talk to her, right? And that's all we're going to assume, except for one caveat. Bob B prime should be able to do this independent of any history of conversations so far. It is not useful if every time you ask Alice, she faithfully answers the question. So you ask a question, 0 or 1 is the answer, but then she tosses a random coin in her head which is fixed for each unit of time and then XORs it with the question that you asked. So if you had the opportunity to ask her 2 questions at the ith unit of time, then you would get very useful information, but unfortunately the restriction is we can only ask her 1 question at a time. So though she is actually in principle answering these questions, there's no way of effectively getting it out of her. So really what you would want is, even though she's been carrying on a conversation, reached a strange state of mind, Bob B prime should be able to talk to her, not in one question, not say give me the answer to X, but rather start interacting with her, ask her a few questions, get her attention, get her to understand that that Bob prime's interest is in deciding X and S, and be able to get the answer to that. We would like this to happen for some Bob B prime. So should be able to, at any given time of the day, be able to talk to Alice for a while, for a feasible amount of while, and then be able to get the answer. Okay, does this make sense? So that's the only assumption. Alice should be helpful in this sense. Now she's being helpful for the same problem that Bob wants to solve, and people come back saying, isn't that unrealistic? Why should it be that she's interested in solving the same problem? She's not. She's interested in solving any problem you're interested in. She's capable of solving the problem S. She would be happy to take some other problem S prime and solve it for you. Some other problem S double prime, also solve it for you, if that's what you want. But she has to be able to solve the problem that you are interested in, or else it's futile to get her to solve it for you. So that's all this definition requires. Not that she knows that you're interested in solving this problem, but rather that she's able to solve that problem if she's given the information that this is what you're interested in. Okay. Any questions at this stage? So this is a definition of being helpful and cooperative and intelligent. Now what is successful communication? Well, informally it's again very simple. There should be this Bob who can talk to any S helpful Alice. One single Bob, single algorithm which works for any helpful person, and with all of them is able to eventually use them to solve S. Okay. So Alice is speaking a different language, it's a different S helpful Alice, still the same Bob should be able to talk to her and get the answers out. So that's the definition. Formally it says the following. So you have to, I'll sort of state it in two ways. There should be completeness and soundness to this interaction. Bob is what's called S universal, can solve S no matter which Alice he's talking to. If whenever he's given a problem instance X and he wants to decide is X an S or not, if X is an S, Alice is helpful for S, then Alice and Bob should interact and Bob should accept. If on the other hand Alice and Bob interact and they are accepting with very high probability, then X should be in the language. Okay. There is a little bit of a parenthetical remark over here, and Alice is helpful. So really let's consider the case where Alice is helpful. There is no question of mistrust. She wants to help Bob. She will not lie deliberately if she knows what he is interested in. Okay. She will not try to mislead him. So in principle, with such an interaction, you could solve the spam filter problem. You ask Alice, is this program a spam? Is this email a spam? She tells you. You could ask the safetiness of a program. Is this program a virus or is it safe? And she will tell you if she understands the question. There is only the slight possibility that she may not understand what you are saying, and so we would like to know, can we do anything with that? So if Alice is virus helpful, then she will help you, tell you which ones are viruses and which ones are not. Question is, can you build a virus helpful virus universal Bob in such a case, right? Who can talk to this thing? And our theorem basically says no, you cannot get a virus helpful Bob, but you can get a chess helpful Bob. I'm sorry, a virus universal Bob, but a chess universal Bob is possible. So there is a person who can use this kind of infinite wisdom to solve problems that they couldn't otherwise solve. And the problem happens to be chess. It's a p-space complete problem, and if the theorem basically says if you have a p-space complete thing, then there are many other problems, by the way. You could also factor integers, you could solve satisfiability, there are many other problems. Chess is a good example. It's the sort of the most powerful thing that you can solve by asking for help from others. And there's a very interesting, this is a sort of a theorem and its converse. Let me start with the converse first. If there is an S universal Bob for some problem S, then this problem is in p-space. Okay. And this is, I think, an interesting result because it tells us that when we are doing these spam filter thing, there's a lot of trust going out there. Okay. You're really hoping that your internet interactions you're really trusting everything out there, your DNS, who it points to, the information that you're getting, because you cannot on your own verify whether this thing was a virus or not, even with the help of the virus detector. While on the other hand, if somebody was giving you help saying, I can help you play the optimal moves in chess, you don't have to trust that person, you don't have to understand that person, and you don't have to do that. You just have to, you carry on an interaction, you can confirm your guesses, okay, and confirm any assertions made by the other person. So there is a dichotomy here. By communicating, you can enhance your computational power somewhat, but not to an unlimited extent. Okay. So that's the theorem. There's a little bit, just basically repeats what I said in English. The only thing that I want to point over here is we don't prove a strong technical theorem here. The technical theorem was proved about 15 years ago or even earlier by Lund, Fortno, Karloff and Nissan, and then by Shamir, who showed that interactively you can prove solutions to many problems that you couldn't solve on your own, and that's the theory that we are using. So let me tell you briefly a little bit about this interactive proofs and the theory underlying. What is it? It's a very similar setting. There's an Alice and there's a Bob when they're communicating with each other, and Bob is trying to solve some problems and Alice is trying to prove some statements to him, and they're trying to figure out, Bob wants to be able to at the end of the interaction be able to tell whether this, whether he has a valid solution to the problem or not. The thing that's different in their case and ours, the case between interactive proofs and our universal communication setting, is that in their case Bob does not trust Alice. Okay? In our case, trust is not an issue. We're happy to say, look, I'll trust this Alice, let me just try to see if I understand her, but I don't understand her. And the theorem that we have basically says that in either case, we can solve p-space problems. Bob can solve p-space problems. So whether it's mistrust or misunderstanding that's leading to this miscommunication, it's the same thing. You can still solve the same set of problems. And let me tell you briefly how we use this thing. So roughly what we are going to use is the theorem proved by Shamir, which said that any problem in p-space, I can prove interactively to you what its solutions are. So I give you a solution and I say, look, X is in the set S, and let me prove it to you, and Alice can start proving this to Bob, and Bob, who doesn't trust her, carries on this interaction, at the end is convinced that no matter what Alice's intentions, the statement is true. And we are going to try and emulate this interactive proof in our setting, where Alice doesn't understand X, doesn't understand S, giving some answers to some questions, we don't know what, and we are somehow going to extract answers out of her. How are we going to do this? So let me tell you a little bit about the proof. So this positive result, which is all I'll tell you about, is based on the following setting. So Bob is sitting out here and is trying to talk to Alice, and he has no clue what to do with her. Okay? So what's he going to do? He's going to generate this program that he calls an interpreter. Okay? And he's also, let's say, he's going to, he's got an instance X, he wants to prove he wants to verify a proof that X is in the set S, and he has this, he's going to build an interpreter. Okay? So he's going to write a computer program called an interpreter. He's going to say, well, let me try using this interpreter, and let's try using him to talk to Alice. So I'll send my questions to the interpreter. The interpreter will translate those questions and forward them to Alice. And now what Bob does is he puts a box around those two together, the interpreter that he created, the Alice that exists out there, and say, that's my prover. That's the person who's going to try to prove to me that X is in the set S. Okay? And Bob talks to this prover, this red arrow saying Bob is now trying to talk to this prover and get this prover to convince him that X is in S. Okay? And he carries on an interaction with this prover for a while. How is this interaction happening? The interpreter is passing on messages. How did you come up with the right interpreter? Wait, you'll see. So Bob carries this interaction. At the end, what happens? You come up with a convincing proof that X is in the set S. What do? You just say, hey, I'm happy, solved the problem, I'm done. I don't need to do anything further. Was the interpreter right? I don't know. But the interpreter managed to find a convincing proof that X is in the set S. I'm done. On the other hand, if this interaction failed, which is pretty likely the first thing that will happen, you created an interpreter, had no knowledge of Alice, and you started doing this interaction, what do you conclude at the end when the interaction fails? Well, you have to be forgiving. Okay? The reason this thing did not work is not because Alice is trying to cheat you, it's just because you don't understand her. So your interpreter was wrong. So this interpreter is ruled out, we try the next one. And remember, this is where we're going to use the fact that there's only finitely many possibilities for the interpreter till we come to the right one. There is an interpreter out there. Why? Because Alice is helpful. Somebody can talk to her and get answers to questions from her. So that person will eventually emerge, and with that person we can actually start talking to Alice and get convincing answers. So this is not a remarkable theorem or a proof, but I think it's a very important one in the sense that it's saying that once you lay out your goals, saying, look, my goal for communication was not to understand Alice, but really to solve problems that I understood on my own and was able to even verify claims about them on my own. Once you were so concrete about your problem and your goals, the fact is you can sort of try various plausible strategies with Alice, and when they work, it's good, you've already solved your problem, you're happy, you move on. And when they don't work, you say, well, I haven't understood her perfectly, so I make progress in a different coordinate. I get closer to understanding her. And eventually, there's a finite length string which will convince me completely what Alice is. Now, for any pair, any Bob, if you lay out a bound saying, this is how large I'll allow my interpreter to be, this is how much time I'll allow for the conversation to take place, there will be an Alice out there which will take even longer to learn. So this is, you can never put a firm bound saying, I've learned Alice. This is never going to happen. This is no more likely than if you could go home to your children and say, I've completely understood my child, or completely understood your parents. You never do. They are intelligent beings. You're never going to understand them perfectly. But to the extent of the goal of this communication, you have been able to understand them. That's what we wish to achieve, and that's what we are achieving. So the negative result, I have a few lines in the proof, but I won't get into it. I want to address this one question again. So is this really language learning? Notice the first thing that we did after we came to this sort of computational goal was dismiss the question of learning languages. I don't want to learn languages. I just want to solve my problem. But I claim that we are still learning a language. Wow, there is this interpreter that we are building. If he's managing to make feasible progress with Alice, then it's probably good to use on the next problem, right? Next I have an X prime, I want to know, is it an S? Hey, let's use the same interpreter, it's going to work. If it doesn't work, well, keep marching along. You're making progress. Eventually you're going to get this ultimate interpreter who's going to work. And that interpreter is, finally telling you how to translate your questions from Bob to Alice. So in some senses you are learning the language, and I think this may not be the right interpreter, but that's actually excellent news, because if you're looking for the right interpreter, I can prove it's impossible, but this one works as well, and you can never tell it apart from the wrong one, from the right one. So why bother, right? I mean, if this is satisfying all your goals, then you should be happy. So this was a concrete instance of a goal. We developed it carefully and fully. There were no deep theorems, and there are no deep theorems coming up further either. But I just want to say that actually by now we've almost solved the computational problem. And I could talk about lots of other goals, but they're all captured in very similar spirit. So let me tell you a little bit about what are other goals. And once again, I want to stress that this is something that hasn't been looked at explicitly. What I'm listing over here is just some examples that I came up with and we came up with, but maybe there are other examples. If they don't fit in this picture, I would love to learn about them. If they do fit, then also I might love to learn about them. So the remote control example, my computer wants to print something on a laptop. That's a good example of remote control, right? We want to effect a physical action remotely by sending some signals. We want to buy something on Amazon. That's also equally remote. I mean, what's the goal? I want to type some sequence of bits on my computer, and next day the UPS guy should deliver something in my doorstep. What happens in the interim is not my concern. So it's a very verifiable goal. There's also other forms of things. When I'm talking to you, maybe I don't have a laid out thing saying, I would like to solve this problem in today's talk by talking to Zig here or something. So I don't have a necessary well-defined goal, but I'm still very curious to say, maybe I will learn something. I don't have a given target. Is that a verifiable goal? I claim if it is not verifiable, then you shouldn't be engaging in this conversation. At the end of the day, I've had this conversation, I can always evaluate it on my own and say, was this happy? Was it a good, satisfactory conversation, or was it not? If I can evaluate it, then there is an explicit function of the interaction and my state of my brain that tells me whether the interaction was successful or not. That's a verifiable goal. So really there are many other things that you can lay out, and all of these are reasonable goals, but I claim they're all something that we can fit in this setting. And the way we fit it in the setting is by defining what we call a generic goal. Goal is a function of Bob's private input, his random coins that he tosses, the interactions with Alice, but also maybe the interactions of the interpreter with Alice and my interactions and Bob's interactions with the interpreter. All of these things are happening in this universe, and you can follow all of this. And it's also a function of the environment. For example, Alice prints on a sheet of paper, and Bob can look at that sheet of paper and see if this is what he wanted to print. So the environment is being affected by Alice. It can be sensed by Bob, and you can throw all of this into the mix and say the goal is a function which is efficiently computable of all of these things which Bob can see. And in order to make it a useful goal, it should be verifiable. Bob should be able to look at all of this and say, is this satisfactory or not? Has my goal been achieved or not? And this should be efficiently computable. It should be complete in the sense that if Alice and Bob have a common language, they're already talking perfectly, then Bob should always be satisfied. This is what we would like. And it should be non-trivial in the sense that Bob should not be able to just achieve it without Alice's help. Right? If he could achieve it without Alice's help, he should not try to delude himself into thinking that he's understanding her and getting her help to solve the problems, because he might well be solving them on his own. So really, he should not be achievable without Alice. And that's what makes it a goal. And so in this generic goal setting, really we have these three players: Bob, an interpreter that he creates, and the Alice. The interpreter converts sentences that Bob, instructions from Bob to interactions with Alice, and uses that interaction to answer Bob's questions, who generates more questions, and you continue this process. At the end, Bob applies a verification function to his private inputs, his randomness, and the interactions that he saw. All of these interactions, all of those, and put everything together. And if you put all of these things together, you get Bob's goal. Now, it's not very useful to say, well, I have this goal and can be satisfied by a different Bob. Really, Bob is fixed. What do we want to be universal is this interpreter. The interpreter sitting in the middle is the quantity that we're really focusing on. We want a single interpreter which will work for all Alices with respect to this fixed Bob and the fixed verification, fixed goal that you're trying to achieve. And if there is such an interpreter that works for all possible Alices, that's the universal interpreter that we are looking for, and that's the one that we want. And I claim that almost all the examples that I mentioned on the previous slide, the printer, the buying something on Amazon, or listening to music, all of these things can in some form or the other, music, I'm not sure we've sort of figured out the computational issues of why some tunes please us or not, but assuming there is a sort of a computer acting on a sequence of bits and saying, well, is this pleasant music or not, and can decide that, well, we can start looking at such issues as well. And those are goals that we can achieve. Get to hear good music by figuring out the right interface. Is this a Windows media player file, or is it a real audio file, etc. You should be able to figure these out by enumeration and keeping your goal fixed and applying them. So a goal in this generic setting is given by Bob, a class of interpreters and a verifier, and it can capture all the problems in the previous setting. Okay? So we can define helpfulness with respect to a goal. Instead of S helpful, we have the goal helpful. We have, instead of S universal, you have a goal universal, and the definitions hardly change. And you can prove that there are goal universal interpreters for any one of these goals. So it's true that we still have a lot of work ahead trying to figure out what are interesting goals. But that's the work that needs to be done, not how to translate languages. Language translation is easy. It's the issue of trying to say what are the various goals of communication. And some of these things are actually still pretty interesting. How do you model the printer, or how do you model intellectual curiosity? For example, Bob can say, look, I'm open-minded. I'm just interested in hearing interesting mathematical results. Send me a theorem. And you come up with a theorem. You say, look, this is a theorem. And I think about it for a while, and I say, hey, I didn't come up with a proof. I couldn't prove it to myself. Okay, now give me the proof. Then you come up with a proof. Now this is something that satisfies my intellectual curiosity, the way I define it. And certainly this can be laid out as a goal. And if you want to say this is your goal, this is what you want to achieve, go ahead and you can achieve it with an alien out there. So if this alien is sending bits to you and you want to know, She seems to be reacting to me, let me test it out. So I say, look, send me an interesting theorem. She sends something. And I say, ask for a proof. She sends me something. And it doesn't look like an interesting, a proof of an interesting theorem, or the theorem looks trivial, or the proof looks incorrect. Well, maybe I don't have the right language to talk to her. I'll try the next interpreter. If on the other hand it's working, then great. I say, look, she's starting to give me interesting theorems and proofs. Must be intelligent. So that's the sense in which we can start thinking about intelligence proofs over here. So the conclusion is that goals of communication can be achieved without a common language. And so in 5 minutes I'll try to tell you a little bit about, what about this issue of language. So if common language is not needed, why have we been wasting our time developing English, developing any natural languages? What was the role of language? I think it's a very good question to study, and it should still be studied from the point of view of computational complexity. I think the goal of language is to improve some efficiency, the efficiency of interaction between me and you. I want to solve some problems in my head. I want to achieve a goal. There's a certain number of bits of communication that should be necessary even when we understand each other perfectly with the best languages in mind. And the language design is always trying to make this interaction as minimal as possible. And if we keep this in mind, then maybe we will start understanding what is the role that languages serve in interaction. So it is useful. It reduces the number of rounds of interaction between you and me. Maybe it helps reduce the total number of bits of communication. I don't know the exact role either, but I think it's an interesting question. We should examine it further, but I think it is something that's computationally relevant. And so it definitely is a topic for further study. What is the efficiency measure that languages optimize? And I don't know at the moment that if this measure is sort of asymptotically significant, or is it just a constant number of bits difference. Maybe a constant number of bits, maybe it's asymptotically significant. Whatever it is, it's something that's useful to think about and figure out. Okay, so that's the talk. So just want to sort of summarize with an anecdote. With a joke maybe. We've been working with this atmosphere where we think that the computer and the laptop have to be given perfect, complete understanding of each other. And I want to suggest that there's maybe a different paradigm, and you should try to, lay out your goals and then interactively figure out if we understand each other well enough to be able to achieve the goals. And so maybe the future paradigm for how a laptop sends to file to a printer would be to say, look, the laptop says to the printer, print this file. And the printer will say, yeah, but I want to make sure you understand me, so here's a riddle, can you solve it for me? So in this case it says if there are 3 oranges and you take away 2, how many will you have? And so you try to answer the question, the laptop says, okay, 1 orange, and the printer says, okay, sorry, we don't understand each other. And you look at this question carefully and you say, oh, I got it, the answer is 2, I have 2 oranges. And the printer says, okay, then now we understand each other, now I think I realize that when you say you want to print something, you really want to print that thing, I'll print it. Okay, so that's roughly the model. I want to say that there's a lot of criticisms of this model. People say, where are you going to get this p-space powerful ALS to solve all your problems? It's a good question. I think there's actually the wisdom of the universe, of the human universe, all the other humanity around me is much more powerful than me alone. If I model me as a polynomial time computer, modeling the rest of the universe as a p-space computer is not such an unrealistic assumption. Really, we have to think about it carefully. But that being said, I think it was just an example that we came up with. It works very nicely, but there are many other examples. If Alice can solve n cube time problems, that's all, but the language translation takes only n square time, then I can actually establish communication with her. I can make sure that Alice is solving problems that the interpreter doesn't, and that's already enough to suggest that there's some interesting exchange of information. So we don't need very powerful Alices in this setting. It's just convenient to have that. And there was this exponential time learning. What do we mean by that? I had to enumerate every interpreter and say, is this right or is this not right? Is this right, is this not right? I would be much more happy with a solution which said the time it takes to guess the interpreter is linear in the size of the interpreter. So if you're speaking in French and I'm talking in English, the time taken that it takes me to understand you should not be exponential in the length of the French to English dictionary, it should be linear. So that's something that we should strive for. Unfortunately, in our current modeling, this is impossible. We can prove that exponential time learning is roughly necessary. But basically, I think it's just begging an open question, saying what else are phenomena of natural languages which allow us to learn more efficiently. And there may be a lot out there that we can do. I mean, children do spend about 2.5 to 3 years before they start uttering their first sentences. On the other hand, so they're spending a lot of time learning the language. On the other hand, they're also, that's only 2.5 to 3 years. The exponential time learning does not justify that kind of, it's not that quick. On the other hand, we are talking in a very, very reduced language. And maybe that's all it takes. If you're going to talk to a strange person, you quickly reduce the complexity of your language in your own estimation to something as simple as possible. And you do that, and then the rest of it you throw up your hands and you hope for good luck, and the other person has the same measures of complexity and hopefully will come up with your language very quickly, even though it's exponential time. So maybe that's what happens, we don't know. There's the general question of what are other goals of communication and what assumptions do we need to make to show that this language learning is efficient. These are interesting questions and I think we should look at them. There's a copy of a paper over here, but it'll soon be updated. If you look at it in a week's time, it'll be a much better one. Okay? All right, thanks.
So you assumed a very extreme case where the two objects don't understand each other at all.
Right.
Now, a more common case that arises in daily life, for example, when I buy a new piece of software, that's one object, I have another object, and we do understand a little bit of each other.
Absolutely.
How does that additional information help in solving this problem?
Absolutely. I think so. The additional information can be very useful in turning this hypothetical theoretical solution into an efficient one in practice. So your model can continue to be, at all stages you keep in your state of mind, whenever I'm interacting with somebody, there's a possibility that I don't understand them. Any answer I get from them, I should try to check on my own. But instead of starting to enumerate from scratch and try to figure out who this person is or what's the language to talk to them, I jump to the right point in the queue and I say, look, I'm going to start here and you're somewhere in the vicinity of this thing, and I can search in the vicinity more efficiently and arrive. If you made a small change to your protocol today, then I should be able to get there very quickly. The only thing is, in this case, I cannot keep marching along linearly out to infinity, but I should keep walking back and forth. I should try things that I dismissed yesterday because you changed your language.
Like side information, yeah.
Right, exactly. So you have a little extra and yeah.
When you're expecting exponential time learning, how can you differentiate between an interpreter solving the problem for you and the other party having some intelligence?
Sorry, yeah, there was a technical thing that I missed over here. There are two issues over here. One is the length of the language, or the compiler of the language, and the other is the problem that you're trying to solve. Now, an underlying hypothesis over here was the language is constant sized or some finite size, and the problems that you're solving are huge. I think it's a reasonable interpretation of language that you build small languages relative to the amount of time you're intending to use them. There's no point building a huge vocabulary if you don't expect to use all the words in it at least once. and presumably every word should be used infinitely often, or else why should I even bother to include that word in my vocabulary? I might as well just use its expansion. So there is an assumption that there is a small language, a huge problem that we want to solve, and relative to the size of this huge problem, the interpreter is solving it quickly because exponential time in that huge thing would be really, really, really large. But there is a small size of the language, which in our model we just said is a constant size. You run in time exponential in that in order to solve the big problem, which is still okay because it's still sublinear maybe in the size of the problems that you're trying to solve, because there's two parameters. One of them is small and I'm exponential in the small one. The big one is the length of x, that's huge, and so it's okay. But really a more convincing solution would be when the length of the language is allowed to be somewhat growing as a function of n, and I have to understand how large it is relative to the size of the problems that we are trying to solve. I would prefer a polynomial relationship between the length of the language and the problems being solved.